Picture a typical late-night study session. You're at your desk, the books are piled up, your notes are scattered everywhere, and your bedroom is reaching that familiar, cozy state of clutter. Right next to your notebook, there's a glass of iced coffee. If you watch it long enough, you'll see the condensation drip down the sides, and the ice cubes shrink and melt away into the liquid. We see these things happen every day, but have you ever wondered why? Why does a clean room eventually get messy, but a messy room never accidentally cleans itself? And why does that ice melt into a puddle, but the puddle never spontaneously freezes back into cubes? Every time your coffee warms up or your room gets cluttered, you're seeing the direct result of the universal laws of thermodynamics. These rules aren't just for industrial steam engines or rocket scientists. They are the invisible framework that dictates the flow of energy in our everyday reality. To understand how this works, let's look at the wall of our messy bedroom. Imagine there's an old-school thermometer hanging there. If that thermometer has been resting there all day, it has settled into the exact same temperature as the wall. And the wall, naturally, is the exact same temperature as the air circulating through the room. This diagram shows a simple mathematical chain. Because the thermometer is equal to the wall, and the wall is equal to the air, we know for a fact that the thermometer shares that exact same temperature with the air. Physicists call this state of perfect balance thermal equilibrium. This is the zeroth law of thermodynamics. It defines exactly why a thermometer can accurately measure the world around it, giving us a reliable way to define what temperature actually is. Now let's look back at you and your coffee to see the first law in action. This rule states that energy can never be created out of thin air, and it can never be destroyed. It can only be transferred from one place to another. To track energy, we use internal energy. Zooming in on that coffee, we see millions of atoms colliding. That buzzing motion is internal energy. This acts like a snapshot of current settings: pressure, volume, temperature. The universe only accounts for how much energy it has right now. There are exactly two ways to change those settings. The first is heat. Heat is energy transfer driven by a difference in temperature, like warm bedroom air giving its energy to your cold drink, melting the ice. The second way is work. Work is energy transfer through physical force, like when you push your chair back from the desk or press a pen into your notebook to write. You and your coffee are constantly exchanging heat and work with the bedroom around you. But if you added up every single drop of energy lost and gained in that room, the total Vangda count of the universe remains exactly the same. But here we hit a contradiction. If energy is perfectly conserved, why doesn't your melted coffee spontaneously absorb some work from the room and freeze itself back into solid ice cubes? That brings us to the second law of thermodynamics and the concept of entropy. Entropy is the rule that all systems naturally move towards disorder. This chart shows why entropy always increases using probability. On the left, there is one specific way for a system to be perfectly ordered, but on the right, there are billions of ways for it to be a mess. Disorder is vastly more likely. This probability is why heat only flows from hot to cold. Energy naturally scatters and spreads out across the room because it is incredibly unlikely to randomly clump back together inside your coffee glass. This connection between the microscopic probabilities of atoms and the macroscopic world of heat was famously established by physicist Ludwig Boltzmann. Because of his work, we understand that entropy is the reason your bedroom gets messy, ice melts, and the arrow of time moves strictly forward. What if we wanted to stop all this increasing disorder? What if we wanted to freeze entropy completely and hit pause on the universe? According to the third law of thermodynamics, you would have to drop the temperature to absolute zero. At that point, all molecular motion would cease. But there's a problem. As a system gets colder, it takes more and more effort to remove each remaining bit of heat. Think of it like trying to empty a room of air using a pump that gets weaker the more you use it. You can make the room emptier, but you'll never reach a perfect absolute vacuum. Because absolute zero is an unreachable limit, the universe will always retain a tiny fraction of motion and entropy. Reality will never let you hit the ultimate pause button. Let's thaw out our bedroom and bring it back to a warm, buzzing state of normal, everyday activity. The thermometer balancing on the wall, the physical work at your desk, the ice melting in your glass are all playing a cosmic game. The laws of thermodynamics are the beautiful, unstoppable engines driving